Thank you for the opportunity to speak in this series. So I'm going to tell you about some work that we've been doing on the East Pacific Rise 950 North segment, which is very well studied. And so I have the benefit of being able to build on many decades of some excellent science. And what I'm going to tell you about today is some work that I've been doing with my students at Scripps, including Jinnai Wu, Zoe Yin, and Natalia Berrios Rivera. And also my collaborators, Dan Fenari, Thibaut Bayer, and Jill McDermott. And to get us started, what we're looking at here is a photographic image of the 2005-2006 lava flow at 950. And so you can see these pillar structures and collapses on this lava flow that was in place around 15 to 16 years ago. And we're going to spend most of our time today thinking about this 2005-2006 eruption. So to begin with, I'm going to tell you a bit about the 950 North segment, which I suspect quite a few of you here know already quite a lot about, but hopefully this will be a little refresher. And then we're going to spend most of our time working out methods to calculate an accurate estimate of the volume that was erupted in 2005-2006. And hopefully we'll be able to say something about how much of the melt that was removed from the axial magma chamber ended up on the seafloor and how much ended up remaining in the crust. And then in the last few minutes, I'm going to show you some of the work that we've been doing to monitor the hydrothermal vent system at 950 in an effort to try to forecast when the next eruption is likely to happen. And so this photograph I'm showing you right now is one of our autonomous temperature loggers that we've left on the seafloor for the last several years. And you can see, hopefully you can see my mouse, this temperature logger sits with a titanium probe in the orifice of these high temperature vents. And I'll tell you more about that towards the end. So to begin with, for those of you who are not so familiar with the East Pacific Rise, this map shows the global mid-ocean ridge network, and I've colored the seafloor here according to spreading rate. And we're going to be focusing in on this little segment over here where this white box is, and the spreading rate here is about 110 kilometers per million years. So it's a fast spreading mid-ocean ridge segment. And it's a place that has been studied for very many years, and it's one of those places where several major discoveries have been made in terms of understanding how oceanic crust is formed. And so it's been an area of great focus since really the 1970s. So if we zoom in on this 950 segment, it's bounded to the north by the Clipperton transform and the south by the Siqueiros transform. And we have these giant Lamont seamounts which intersect the mid-ocean ridge here. And this 950 segment has in the middle of it this nice overlapping spreading segment. And the area we're going to concentrate on today is this area that I'm just pointing out right here with my mouse. So people have been making breakthrough discoveries here really since the 1970s. For example, this is one of the very first times that we've been able to use seismic reflection imaging to image an axial magma chamber. So this is a pair of images collected by the group at Lamont in the 1970s and 1980s using the Robert Conrad. And this image on the left is from a paper in 1978 where you can see very nicely, well, to get your eye in the seafloor reflection is where my mouse is here. And very nicely, you can see this R4 reflection, which at the time was thought to be the top of a melt lens. And we now know is the top of the axial magma lens at 950 degrees north. And the image on the right-hand side is a follow-up experiment in the 1980s published by Bob Dietrich and others, where you can really see this nice imagery of the axial magma chamber, which we now know is at a depth of around 1.5 kilometers below the seafloor. And towards the end of the talk, I'm going to show you some more up-to-date imaging done by still the group from Lamont, collected in 2008, where we can say something about the melt content of that axial magma lens. So since the 1980s, we now know that this is an actively erupting volcanic system. This is a pair of images published in a paper by Rachel Heyman in the early 90s, where they collected some of the very first in situ live observations of a seafloor eruption. So the image, I know nowadays these images look quite poor, but at the time they were cutting edge. So the image on the left-hand side is from the Argo vehicle, which was the precursor to what is now JASON, which you're going to see a bit later on. And this is an image showing some mussel beds and hydrothermal vent communities living on top of this pre-existing lava flow. And the image on the right was collected 2 years later using the submersible Alvin in almost exactly the same spot. And you can see that all these hydrothermal deep sea vent communities have been totally obliterated and replaced by this glassy basalt lava flow, which at the time they thought was likely to have been in place just several days before. And you can see these white colored surfaces. These are microbial mats that immediately colonized that freshly deposited lava. And so we think that in 1991, we have this large eruption that repaved the seafloor in this area. So since then, there's been another eruption. So in 2005, 2006, there was another significant eruption at 950. And this time we had some more instruments on the seafloor. And these data were collected as part of the RIDGE program. So these are a couple of figures from Maya Tolstoy's paper in 2006. So to get your eye in, this map here is focused on this 950 segment, and these colored dots are ocean bottom seismographs that were on the seafloor at the time of the 2005-2006 eruption. You can see that some of them were recovered, some of them were stuck, and some of them didn't make it through the eruption. And the key thing is that because these instruments were on the seafloor at the time of the eruption, we're able to monitor the buildup of seismicity as this eruption took place. And so this figure on the left from the Tolstoy paper shows the number of earthquake events per day on the y-axis versus time on the x-axis. And you can see that these black dots show that the number of earthquakes increased progressively as we approached this date of January the 22nd, 2006. And so we think this indicated early January, and you see this tail off in seismic activity after that point. And so this is one of the very first times that a seafloor magmatic event had been captured using seismographs on the seafloor. Several years later, those same OBSs were used to detect these what have been called impulsive lava events. So this is a nice paper by Yenjo Tan and others from 2016. And on the right-hand side, you can see these two maps, and there are a bunch of red dots plotted on here, which are those acoustic impulsive events, and I'll show you what I mean by those in a second. And they've been plotted on top of a gray outline. You can see that hopefully there's this gray polygon underneath here, and in this zoom-in map, you can see this gray polygon. That was the best interpretation of the 2005-2006 eruption based on photographic imagery taken before and after the eruption. And you can see that these little red dots don't really match up perfectly well with this 2005-2006 eruption extent. So for example, you can see, hopefully where my mouse is right now, we have a whole bunch of acoustic impulsive events over here that apparently happened outside of the 2005-2006 eruption extent. So something isn't quite right here. This little cartoon down here from Yenjo's paper shows how we think these acoustic impulsive events occur, or at least how they're recorded. So this blue line up here is the sea surface, and this brown line down here is the seafloor. And they imagine that you have some kind of acoustic source, so perhaps a molten lava interacting with seawater. You have an acoustic wave that travels from that source up to the sea surface, and then maybe it bounces a couple of times, or maybe it just bounces once, as shown by this black ray path. And it can be recorded by a receiver, which in this case is an ocean bottom seismograph, which allows us to, with quite good accuracy, detect where those acoustic impulsive events occurred. So this catalog of acoustic impulsive events is very useful, but it seems like the flow outline defined from these seafloor photographs doesn't seem to quite make sense. So what we'd like to do is to understand in more detail just how big the 2005-2006 was in terms of its volume. And also we'd like to know when is the next eruption going to happen. And it's these two questions we're going to focus on for the next half an hour or so. So we've tackled this problem using a variety of methods, and the main one is mapping the seafloor using the autonomous underwater vehicle Sentry, which is operated by the National Deep Submergence Facility at Woods Hole Oceanographic Institution. It kind of looks like a giant yellow bar of soap on its side, but I can tell you it's a lot more useful than a bar of soap. And here it is being deployed off the side of the research vessel Revel in April of 2021. And if we look a little bit more closely, this is a cutout view of the vehicle. You can see the main components consist of a pressure housing, which is in the middle of the vehicle where all the batteries and electronics live. And for the purposes of today, we're just going to be talking about the multi-beam and the Sidescan sonar unit, which are mounted on the bottom of the vehicle down here where I'm pointing to right now. The other key component is Sentry carries an ultra-short baseline sonodyne transducer, orange thing here, and I'll talk a bit about the navigation in a second, and it's critical that we get high-resolution, accurate navigation for this vehicle if we're going to be looking at things like changes in seafloor depth. So I'm going to be telling you about this campaign of dives we've done with AUV Sentry. We've conducted 19 mapping dives with Sentry over the last 3 years during 3 cruises, 2018, 2019, and most recently in 2021. The map you can see on the left-hand side here shows the coverage. So this area that you can see, this colored in bathymetry, is the mapping area that we've collected. It covers about 115 square kilometers, and it's designed to cover the extent of the 2005-2006 eruption. I guess I can cut to the chase here. I've drawn on here this black outline, which is our newly defined outline of the 2005-2006 eruption, which you can see is a little bit different to the one that I showed you superimposed underneath the TAN data set. And in the panel on the right, you can see these little gray dots of those same acoustic impulsive events. And you can see that we've now, with our new interpretation, it now looks like these acoustic impulsive events are all enclosed within this new flow outline. So what I'm going to tell you about is how we've got to this point of mapping this flow outline. And this is mostly work that's been done by my graduate student, Jin-Nai Wu, and we just submitted it for publication in G-Cubed. So hopefully it'll be coming to a journal near you soon in the next few months. So I just want to spend a couple of minutes talking about the navigation of Sentry, and this is navigation of AUVs is maybe not the most exciting subject, but for our purposes, it actually is really critical that we have very well navigated data so that we can be in a position to compare pre and post eruption bathymetry data. So our intention is that we've got this baseline multi-beam bathymetry grid, and then if there's another eruption, we can compare it to a future survey that we may conduct. But nevertheless, what's really important to us is accurate navigation. And so for those of you who aren't obsessed with AUV navigation, the way that we navigate an autonomous underwater vehicle in the oceans, of course, there's no GPS when you're under the water. And so we use a combination of AUV dead reckoning, which is basically a measurement of where the vehicle thinks it is based on its velocity, which is given by this thing called the Doppler velocity log, and also an inertial navigation system. So that measures the attitude and position of the vehicle in the water column. And we combine that dead reckoning with ultra-short baseline fixes from the surface vessel. So this little sketch on the right-hand side shows how that works. So you imagine we have a ultra-short baseline or USBL beacon mounted on the hull of the research vessel, and there's another USBL transducer mounted on Sentry. And every few seconds, we have a ping that goes between the two, and we can get some idea of where, or pretty good idea, where the AUV is at any one time. And typically what we do is take a median position between the AUV dead reckoning and the USBL fixes to get a final position of the vehicle. And usually that depends most heavily on the distance between the vessel and the vehicle, which is another term for that is slant range. So the length of this line you can see here is typically what is determining how accurate our navigation is. As it turns out, it gets a little bit more complicated than that. And so in this sketch, you can see, I'm just going to point out this angle phi, which is the relative bearing between the vessel and the AUV. And it turns out that phi is quite important, and I'll show you why. So we found that there were quite a lot of artifacts in the details of some of the AUV data that we'd seen here and elsewhere. And so we did some data mining to see why that was. And it turns out that there's an azimuthal dependency in the mismatch between our USBL fixes, so that acoustic leash between the vessel and the vehicle, and the Doppler velocity log, or the dead reckoning position. So to illustrate that, in this diagram, on the y-axis, I have what I'm calling delta easting, which is the difference in the easting position from the USBL versus the DVL. And so ideally, this would be 0 everywhere. So they should be basically the same. And this is plotted as a function of azimuth. So this is being plotted as a function of that relative bearing between the vessel and the vehicle. And you can see that it has this marked increase in delta easting at around about minus 80 degrees. And so if you kind of look at that just in this rose diagram here, you can see that in this kind of southeastern sector, we have differences between our two navigation systems that go up to around 20 meters. And so given these differences, it means that we have this increased uncertainty in AUV position. So to overcome this problem, we've come up with a new correction scheme to account for this azimuthal difference or azimuthal error in AUV navigation. So to illustrate that, I'm just going to show you a little patch of survey data. So this is just a little patch of our survey area at 950. These gray lines are survey track lines that Sentry sailed or swam or went along during the data collection. And we're going to think about two specific tracks. This one that's going southward, this black line, and the adjacent one, which is shown in gray, going northward. And you can imagine there's this area shown in this little red box where swaths from those two adjacent tracks overlap. And what we really want is for those two adjacent swaths to match up perfectly for us to get a seamless map of the seafloor. And it turns out they don't match. So as a result of this azimuthal dependent error, we see that when we compare the gray and the black, you can see there's this difference in the southward and the northward depth according to those two track lines. And so if we didn't do anything about this, we'd end up with a bunch of artifacts that would go through our multi-beam bathymetry grids, and you often see this in other AUV surveys elsewhere. So we've got this correction scheme, which I'm not going to go into the details of. If you're interested, then feel free either to get in touch with me, or you can wait for our paper to come out. But basically, we account for this azimuthal dependency by fitting a polynomial function to this error as a function of azimuth. And so we apply this correction, and this panel C down here shows these two adjacent track lines, gray and black, where we've corrected for this azimuthal dependency, and they match up very nicely, meaning that we're able to eliminate these errors in adjacent track line alignment that we would otherwise have come across. So let's have a look at the data. So just to, for those of you who are not so familiar with AUV data, the comparison between AUV data and typical shipboard multi-beam bathymetry data is kind of interesting. So this is a map showing a portion of our study area collected using 30 kilohertz midwater multi-beam sonar on board the research vessel Thompson. These have a 30-meter resolution, so pretty good given on a global sense. And the mid-ocean ridge spreading center is down here where my mouse is. And if we compare that to the Sentry data that has that correction applied, so these data are now gridded at 1 meter resolution using Sentry's 200 kilohertz multi-beam system. And if I flip back and forth between those, I mean, I don't have to persuade you, the difference is very marked. And we can start to see these really remarkable high resolution details in the seafloor that we haven't been able to see before. So to get your eye in, the axial summit trough is where my mouse is pointing along here. And we can see in great detail the axial summit trough itself, but also we can start to pick out individual fissures. So if you follow my mouse, you can see these individual fissure systems coming up through here. And we can see in great detail these lava flow morphologies as they come off the axis. And then in the next slide, I'm just going to zoom in on this one little patch to show you some more examples. So you can see these fissures are really nicely illuminated using this multi-beam system. These fissures are only a couple of meters across and maybe 5 to 8 meters deep. You can see we've imaged this, these lava flows in great detail. And we can compare this to the Sidescan sonar data that Sentry also collects at the same time. So if I show you now, this is a Sidescan sonar image, mosaicked from a bunch of different dives. And this image is at 20 centimeter resolution. So where you see these dark black areas, these are places where we interpret as being sheet lava flows. And you can see they made it quite a long way off axis. And you can see this nice definition between the sheet flows versus the more rubbly, hackly flows over here. And if I flip between these two, because we have this very well navigated solution, you can see that we can get a really nice match between our Sidescan and our multi-beam data. And so it's a combination of these Sidescan and multi-beam data that we've been using to redefine the extent of the 2005-2006 eruption. So the other benefit we have of being in this study area, because there's such a rich array of data already available, back in 2001, there was a pre-eruption survey, multi-beam survey done using this AUV called ABE, which was the precursor to Sentry, which was sadly lost in 2010. But crucially, ABE was used to collect a survey area, multi-beam bathymetry data in a survey area shown by this black box. And if we zoom in on that, this is an area which is extends a couple of kilometers either side of the axial summit trough. And it has a resolution of around 5 meters pixel size. And we can use this pre-eruption survey to compare to our new 2021 post-eruption survey to calculate the thickness and of the flow that happened in 2005 and get towards a volume estimate. So this is the pre-eruption ABE survey. And if we compare that to our post-eruption Sentry survey, we have this black line here that I've plotted with the white underneath it is the outline of the ABE survey. And you can see we repeated that coverage there. And if we take the difference between the ABE and the Sentry data, we should be able to see the thickness of the 2005 flows. And you can see in this diagram, in this map, it's really illuminated very nicely. So the first thing we had to do was downsample the Sentry data to 5 meters, so it matched the Sentry data. And then we needed to we used a cross-correlation technique to spatially match the two surveys. So in this little box A over here, where we think is outside of the 2005-2006 eruption, we use that as our area to match the two surveys together. And these profiles X and Y are shown over here on the left-hand side. And you can see the agreement between blue, which is Sentry, and red, which is ABE, after our shifting using the cross-correlation is very good. And so we're confident that we have these two surveys correctly georeferenced. And so the colors on this map show the thickness or the change in depth, which we interpret as the thickness of the 2005 flow. And so you can see this does a really nice job of defining the extent of where those flow lobes went during that eruption. And in addition, on top of here, I've plotted these little colored dots, which are those acoustic impulsive events from Tan et al. And I've colored them by time in days since the 22nd of January, 2006. So you can see the time progression with the magenta colors are earlier and the blue colors are later. And you'll notice that the impulsive events are now enclosed within our flow outline, but interestingly, they do not extend all the way to the edge of the flow, which is kind of surprising. So in the next panel, we're just going to zoom in on this one little flow lobe where we have this overlapping coverage. And you'll see that in detail, these impulsive events are a couple of 100 meters from the margin of the flow. And they occur over a range of times. So you'll see that the colors of these events, it goes both from magenta all the way through to blue. So we had these kinds of events throughout the 3 or 4 days of the eruption. And also you'll notice that we have this colored bar here that I've plotted. These are an interpretation of the flow morphologies from photographic images taken after the 2005 eruption from a paper by Alison Fundus and others published in 2010. So for example, you can see the edge of our flow really nicely corresponds to these pillar lavas that you can see in the photographic imagery. And so we had this nice correspondence between photographic imagery, impulsive events, and our flow margin. But we still have to explain why these impulsive events don't simply define the edge of the flow, as you might expect, if they were just a matter of the hot lava or the toe of the lava interacting with seawater. The panel, before I go on to that, I just wanted to show you the panel on the right-hand side shows the bathymetric slope from the Sentry data. And you can see there's this really nice correspondence between where we know we have the edge of the 2005 flow and where we have this nicely defined bathymetric slope change. And so that tells us that we can use the bathymetric slope as an indicator of the flow extent where we don't have this overlapping pre and post eruption data. So if we compare our flow thickness to distance from the axial summit trough, in this plot, I should have put the label on this y-axis, but this left-hand y-axis is the flow thickness in meters. And the x-axis now is the normalized distance from the AST for the whole area where we have overlapping pre and post bathymetric data. So we're combining all of our observations of flow thickness together. And on the right-hand y-axis is time in days of those acoustic impulsive events, which are plotted again as these magenta and blue dots. And you can see that the flow is on average around about 1 meter thick until we get to this most distal area. And all these acoustic impulsive events are dominantly located a couple of 100 meters away from the edge of the flow fronts. So in order to explain that, we've gone back to a paper that was published by Engels et al. In 2003, who were looking at the volatile content of the eruption and also the interaction with seawater. And a common feature that we see on the seafloor are these collapse structures. So this is a photograph that was taken just in April of this year. And you can see this, this kind of lobate flow in the foreground, and then you should be able to make out this dark area of collapse where you have this void space. And the best way of explaining these void spaces is that you can imagine that lava might trap pockets of seawater during the eruption process. And that seawater, because it's trapped, becomes immediately vaporized and results in a gas-filled cavity in this area that eventually became the collapse. And in that gas-filled cavity, we have vapor phase fluids at magmatic temperatures. And that means that we have lava, which is still molten, interacting with the vapor, which results in drips that we can see from samples that we can collect from the seafloor. I'll show you an example in the next slide. And as that vapor cools over time, it leads to a collapse. And so we think that this collapse process may explain the acoustic source for those impulsive acoustic events. And this is an example of one of those drip structures. So this is a nice hand specimen. It's about 0.5 meter across that we collected in April this year. And you can see this is, we think this is the underside of one of those collapses. And you can see these nice lava drips. For example, this one right here and over here. And the only way you can generate these drip structures is if you have vapor phase fluids in contact with molten lava. So that was kind of an aside into acoustic impulsive events, but getting back to our main objective of calculating erupted volumes. So this is a similar plot to the one I showed you a moment ago on the left-hand side. So we have thickness with its label in place on the y-axis and distance from the axial summit trough on the x-axis. This solid black line is a Gaussian function that we fitted to all the thickness estimates from the area where we have the overlapping Abe and Sentry data. And the dashed line is the estimate of thickness from a previous study by Adam Sewell and others who attempted to calculate flow volumes. And they used a flow thickness of about 1.5 meters in their calculations. And it turns out that the median thickness that we come up with is only about 1 meter. And so even though this is only a 0.5 meter difference, that's a third less thickness, we think, over the whole area of the flow. And so when we come to do our volumetric calculations, that has an impact. So the next step after we've established the average flow thickness in the areas where we have the overlapping bathymetry, we've revised the flow extent based on starting with the area where we have the overlapping bathymetry, combining that with the acoustic impulsive events, and then using Sidescan, sonar, and bathymetric, both bathymetry and bathymetric slope, to define the extent of the 2005-2006 flow where we don't have the pre and post eruption data. So these 4 panels show an example of somewhere where we don't have the pre-eruption data, and we've defined the outline, which is shown here by this black line here, based on the location of this little cluster of impulsive events, and also based on the margins of this change in slope character here. And then also we have some towed Sidescan sonar data collected by Hui's DSL 120 system, shown here in panel C. And you can see before the eruption, you can see these features pointed out by these black arrows here. And you can see that they survived in the data that were collected after the eruption in 2018 and 2019. And so we can use some of these pre and post eruption Sidescan data to define our flow extent as well. So that flow extent mapping resulted in a map that looks something like this. And we estimate that the flow area was about 50% larger than was previously estimated. And we know, based on work done previously using seismic reflection data, that the axial magma lens in this region can be defined into 3 distinct segments. And I'll show you some data in the next slide about what they look like. But to get us started, we can define these segments based on these discontinuities we see in the seismic data. So we can have segments 4 to 5, 5 to 6, and 6 to 7. And because we can now map fissures in great detail on the seafloor, we can attribute portions of the 2005 flow to individual fissure systems on the seafloor. And these 3 colors, yellow, orange, and dark brown, we can ascribe to magma that was erupted from these 3 segments of the axial magma lens. And this interpretation is in good agreement with the geochemistry of the flow. So these little colored dots here are from a study by Goss et al. In 2010, and they're colored by the magnesium oxide content. And you can see that these 3 flow areas have quite distinct magnesium oxide contents, which tell us that they came from slightly different conditions in the magma chamber. So we benefit from having this fantastic 3D seismic reflection data set to draw upon that was collected in 2008. I'm showing an example of some imagery there published by Milena Marjanovic and others in 2014. So the y-axis here is two-way travel time, and the x-axis is latitude. And so you can see really nicely imaged here is this axial magma lens, which I'm showing with my mouse here. And you can see it can be divided into these various segments. You can see these discontinuities in the axial magma lens that have been pointed out by others before. We also know the melt content of each one of these segments based on some nice 1D waveform inversion work that was done by Min Ju and others in 2014. So armed with this information about melt content and axial magma lens geometry, and our new mapping of the extent of the 2005 flow at the surface, we can start to do some calculations about how much melt was extracted a long axis during the eruption. So this cartoon kind of shows how we can do this calculation. So what we'd like to know are two things. So first of all, we'd like to know how much melt remained in the crust, because we think we know how much ended up on the seafloor. And we'd also like to know how often the magmatic episodes are, so that we can compare that to our forecasts of magmatic cycles based on other observations. So in this cartoon, I've got these three polygons, yellow, orange, and brown, which are based on the seafloor mapping that we've been looking at earlier. And these red arrows are discontinuities in the axial magma lens from the 3D seismic reflection data. So we imagine we've got three axial magma lens segments shown by these red boxes here. We know their geometry based on the 3D seismic volume. And we think that each one of those axial magma lens, in the most simplest case, feeds the surface system via these three dikes, which are shown here in these gray bars. And so what we'd like to know is how much melt remained in those dikes during the eruption, and how often you need to make a dike in order to account for the rate of spreading that we know is happening in this segment of the East Pacific Rise. So we're going to walk through this calculation together. It's a little bit convoluted, but it's hopefully not too complicated. So in this table that we're going to build up, we're going to think about these three segments. So brown, orange, and yellow, segment 4 to 5, segment 5 to 6, and segment 6 to 7. We know the percentage of melt that was extracted during the 2005 eruption from that 1D waveform inversion from Min-Zhu's paper. And we also think we know the thickness of the axial melt lens based on the 3D seismic reflection data. And the thickness is somewhere between 10 and 30 meters, but it's most likely to be only around 10 meters thick. So for the purposes of this exercise, we're gonna go with the 10-meter estimate for axial melt lens thickness. And so based on what we know about the percentage melt extracted, the thickness of the AML, and the length and the width of the AML from the seismic data, we can calculate the volume extracted from the melt lens for each segment. And those are these three numbers, 9.7, 27.6, and 14.6 times 10 to the 6 meters cubed for each segment. Next, we now know the volume erupted for each segment based on the surface mapping that I was showing you earlier, because we know the area of the 2005 flow, and we also have an estimate of its thickness from where we have the pre- and post-eruption bathymetry comparing the Abe and Sentry data. So for each segment, we have an idea of how much melt ended up on the surface. And so the difference between the amount of melt that ended up on the surface and the melt that must have been extracted from the melt lens must be the volume of melt that remained in the dike between the melt lens and the seafloor. And that's shown by these three numbers here. So now we're making some assumption about the height of the dike, which is simply the depth to the axial magma lens, and also the length of the dike, which we assume to be equal to the length of each axial magma lens segment. We can estimate the dike width if we assume that a single dike is responsible for each segment's eruption. So these three numbers, 1, 1.9, and 0.5 are our estimates of dike width based on this line of logic that I'm showing you. And these dike widths are consistent with previous estimates, both in papers like Zhu et al., but also from observations we can make in the field in places like Oman, where we see dike widths that are consistent with around 1 to 2 meters. So the final step is that if we know that the full spreading rate must be 110 millimeters a year, and if we assume that all the spreading has to be accommodated by magmatism, and of course there might be some component of faulting, but for the purposes of this exercise, we're going to assume that everything is accommodated by magmatism, we can calculate the episode time, or the time between magmatic events, in order to give us this full spreading rate that we know must have some time averaged requirement. And you can see that for segment 5 to 6, we end up with a magmatic episode time or interval of around 18 years, which is consistent with the time between, for example, the 1991 and the 2005 eruption. So that seems to make sense. But what we see for segment 6 to 7 and segment 4 to 5 is a much shorter interval, so 4 and 9 years. And we know, because we've been visiting this site over the last couple of decades, that we have not seen eruptions on this short timescale. And what that implies is that segments 6 to 7 and 4 to 5 are likely to be experiencing these more frequent magmatic episodes, but they probably just result in dikes being in place and not resulting in seafloor eruptions that we can see using observations with submersibles and ROVs. So to summarize so far, we've mapped the 2005-2006 eruption, which is about 50% larger than the area is about 50% larger than we thought before. But the flow is only about 1 meter thick, so it's about 30% thinner than was previously thought. And that means that the total erupted volume is broadly consistent with what has been thought from previous estimates. That little line of logic that I just walked you through in that table shows that around nearly 60% of the melt that was extracted from the axial melt lens remained in the subsurface in the form of dikes. And that means that our magmatic episode interval, or the time between magmatic episodes, ranges between 4 and 18 years. So it has quite a bit of variability along axis, and that the segments either side of the main segment 5 to 6 are likely to be experiencing more frequent diking events without seafloor eruptions taking place. So in the last 5 minutes or so, I just want to give you a taster of some of the monitoring work that we've been doing alongside all of this mapping. And we've been mainly using the ROV Jason, which is shown in this photograph here, and the submersible Alvin. And we're primarily doing two things. We're continuously monitoring the temperature of the hydrothermal vents using time series data that we collect using autonomous loggers, like the ones I showed you earlier on. And also we've been collecting in situ fluid samples every year for the last 3 years to monitor how the fluid content of the vent fluids has changed through time. And we can use that to try to track the depth at which the hydrothermal fluids are circulating. I'm not a fluid chemist, so I'm not going to attempt to cover the fluid chemistry today. So I'm just going to tell you a bit more about the vent temperatures. So this is a photograph of inside the Jason van in April of this year. And I just wanted to give a shout out to NSF for paying for us to have an enhanced satellite bandwidth connection this year, which meant that we were able to live stream all of our Alvin dives via YouTube, which was very successful. And so we were able to share with the public what we were doing out there this year. And this is a photographic image of one of our isobaric gas tight samplers taking a sample of this vent. I think this is P vent at a temperature of around 370 degrees. So this little metal tube you can see here is inserted into the vent orifice. And then we open an actuator, and the vent fluids are collected in these pressure casings that you see up here. So over the last 3 years, we've been continuously deploying and recovering these little autonomous temperature loggers. We have about 25 of them in place at the moment, and we'll be recovering and replacing them again in March of 2022. And here you can see one just sitting, minding its own business in M vent right here. And they continuously log until we come back and collect them during deployment and recovery cruises. This is what those loggers look like before they're deployed. So they're pretty simple. We have this titanium tube. And then in here, there's a pressure casing, which has the electronics and the batteries. And then this is a little lump of syntactic foam that maintains it in place, hanging off the vent orifice. And this is a little collection of those loggers after they've been recovered. You can see that some of them do very nicely and come back in great condition. And then some of them just get totally obliterated by mineral deposits and vent junk as we get them back. And here's a hint of some of the data that we've been collecting. So this is a figure from my colleague Thibaut Bayer, who's in Norway, showing the temperature series at a pair of vents, Bio9 and P vent, over the last couple of decades. So the y-axis on this plot is temperature in degrees, and the x-axis is time. So this record begins in the early 1990s and stretches up until today. And all the little points on here are either spot measurements of temperature collected by a temperature probe on a vehicle, or they're time series data collected by one of those temperature loggers that you can see. And these data are pretty noisy, but you'll see that on the top axis here, we've marked a couple of the eruptions. So this is the 1991 eruption, and this is the 2005 eruption. And you can see that we have this gradual increase in temperature at a rate of around 2.2 degrees per year in the build-up to that 2005 eruption. And the temperature at Bio-9 and P-Vent was just over 385 degrees, just prior to the previous eruption. You can see that temperatures dramatically fell in the time immediately after the eruption. And then since then, they appear to have been increasing again. And up until the end of 2020, you can see this last data point where we start to approach this magic, perhaps 385-degree point, where we might expect to see the next eruption. And so we're going back in March of 2022 and also later in 2023. And we're hoping to have a nice temperature series as we build up to this next eruption. So I've been talking at you for quite a while now, so I'll wrap it up here. But in conclusion, we've seen that a significant portion of the melt in these eruptions remains in the crust, and so we don't see any evidence of them on the seafloor. And our seafloor mapping and that little simple calculation I showed you implies that we have these relatively frequent diking events in segments 4 and 5 and segments 6 and 7. And the temperature logger data shows that we are expecting to be approaching this threshold above which we might expect to see the next eruption. And the mapping data that we've collected very carefully with this careful approach to AUV navigation means that we're in a good position with a baseline map that we can compare to a new data set that might be collected after any eruption that happens in the future. So thank you very much for listening, and I'm happy to take any questions.